Hello.
Good afternoon. Hello, is my voice audible?
Well,
Is my voice audible? Where are other
yes, sir.
students? Okay, where are they? Where is Raghu, Stesh?
They didn't come yet.
Okay. So shall we start or wait few minutes?
We'll wait 5 minutes, so they might come now.
Okay. All right. So let's start our today's class. So in the yesterday's class, we have just discussed about the Planck's quantum theory, right? And in that
Yes, sir.
Planck's quantum theory, we have just seen that whenever any energy is emitted or absorbed, it's always emitted or absorbed in the form of small packets of energy known as quanta. And quanta, it is plural actually, singular is quantum. And in case of light, these quanta are known as photons, right? And then I told that energy of each quantum, it is directly proportional to its frequency. And then I told that whenever a body absorbs or emits radiation, it always do so in the whole number multiple of quanta. So that is E is equal to NH nu. Now, with the help of this Planck's quantum theory, we can explain the two very important phenomena, that is the black body radiation and the photoelectric effect. So let's see. So as we have seen in the black body radiation, that whenever we have, let's say we are having an iron rod, and I have told you that this iron rod, when it is heated, it changes its color. So it first becomes dull red, and then it becomes red, then it becomes yellow, isn't it? Then it becomes white, and then blue. So why it actually changes the color? So let's see what is the reason given by this Planck's quantum theory. So according to Planck's quantum theory, it says that energy is directly proportional to the frequency. So that means higher the frequency, higher will be the energy, right? And we also know that frequency is inversely proportional to the wavelength. So that means higher the frequency, lower will be its wavelength, shorter will be the wavelength. So now if we apply this concept on this black body radiation, we have seen, for example, if we were having an iron rod. So any iron rod, when it is heated, it first becomes red in color. So why it becomes red in color? It is because actually we know that we are having 7 different colors. So first color we were having the violet, then it is the indigo, then it is the blue, then it is the green, yellow, orange, and red. Now we know that red color, it is having very high wavelength. Is
எதுக்கு சார் கிக் அவுட் பண்ணி வச்சிருக்கீங்க? என் தோஸ்த் எங்க?
டேய் கிளாஸ் ரெக்கார்டிங்ல இருக்கு, வாயை முட்டுக்காரு.
நன்றி.
assembly practice.
பாஸ்கெட்பால் பிராக்டிஸ்.
Assembly.
நைஸ்.
So can you hear me? Is my voice audible?
Yes, sir.
Okay, but I can't share the screen. Is there Bhaskar, sir? Just tell him to make me the host so that I can share the whiteboard screen.
Sir, Bhaskar sir isn't outside, sir.
Yes.
Bhaskar sir isn't outside, sir. 1 minute, sir.
Okay. You just make me the host there so that I can share the screen. Is there any option?
Sir, actually, the host control isn't with us, sir. It's with Amrisha.
So, where is the Amrisha?
She's online.
Hello.
Okay.
Hello. Hello, sir. Can you hear me?
Yeah, I can hear you.
What am I supposed to do?
You just make me the host so that I can share the screen. I can share the whiteboard.
How should I do that?
You just click on my name there, and then there will be option to make me the host. Just make me host there, or the admin, host or the admin. Is there any option available? Okay, yeah, it's not correct. Thank you. Okay, so yeah, right now. So I was just saying about this Planck's quantum theory. So with this Planck's quantum theory, we can just explain the black body radiation. So now we know that black body radiation. So in this black body radiation, we can explain that why an iron rod, when it is heated, it becomes first red, and then why it changes its color. We know actually from this Planck's quantum theory that energy of each quantum that is directly proportional to the frequency, isn't it? E is directly proportional to the frequency, and similarly frequency is inversely proportional to the wavelength. Now, why there is the color change in case of iron rod when we just heat it? It is because actually we know that in case of this waveguide, that is the 7 different colors, the highest wavelength is possessed by red color, isn't it? We have already seen this in the yesterday's class that highest wavelength, it is just possessed by this red color. So that means when it has very high wavelength, so that means its frequency will be low. When frequency is less, so that means its energy will also be less, because we know that if frequency is less, so that means energy will be less. And similarly, if wavelength is very high, then frequency will be very low. Now it is the only color red which has very low energy. So now when you just actually heat this iron rod, it firstly becomes red. Why? Because first you are giving minimum energy. So the minimum energy is actually possessed by this red. Now, if you just increase the heat energy, that means if you are increasing the energy, you are giving more and more energy, then its color will change. So that means it can become orange, because orange is having very high energy as compared to the red. Orange has high energy as compared to the red. So that is why it is first becoming red, and then it becomes orange. And similarly, if you further heat, it can also become yellow. And similarly, if you further heat, that means you are just increasing the energy. And we know that when you actually move from this red towards the violet, energy increases, isn't it? When we move from a red color towards the violet, what happens to the energy? Energy increases. We know that. So that is why actually whenever we just heat this iron rod, we are just increasing its energy. So first energy was very low. So that means color will be red because its energy is very low. Then when we just increase the energy, so that means it will change its color. It will become orange, and then it can become yellow. Then it can also become green and blue, isn't it? So that is why this was the actual reason given by this Planck's quantum theory, that whenever any black body, it is heated just like the iron rod, whenever it is heated, so it first becomes red, because red is having very low energy. It is having very high wavelength, or you can say it is having very low frequency, or you can say it is having very low energy. So when it has very short, very small amount of energy, so that is why color will be red. And then when we just increase the energy, its color will become orange, and then yellow, then green, then blue, and then indigo also. So this was the reason how to explain this black body radiation. And next is the photoelectric effect. So shall I move to the next page? Have you written down this?
Sir,
Okay. So next is the photoelectric effect. That's very important. Photoelectric effect was also explained by this Planck's quantum theory, photoelectric effect. So in this photoelectric effect, we have already seen that whenever light falls on the metal surface, for example, let's say this is my any metal surface. Let's say this is my rubidium here, or be rubidium. And when light actually falls on this, let's say this is the light here falling on this rubidium. So what will happen? Electrons will get ejected, right? And this ejection of electrons from the metal surface, it is known as photoelectric effect. We have already seen this. Now, what is the reason? So how actually this Planck's quantum theory explains this photoelectric effect? So according to Planck's quantum theory, it states that actually when we are just giving this light, so this light has some energy. That energy is actually given to this electron, which is here on the metal surface. Some energy is absorbed by this electron, and when this electron, it actually gets ejected from the metal surface, then the rest energy is involved in the kinetic energy. So I will just write it like this, that energy of light, or we can say the energy of photons, it is used in two things. One is the binding energy. That means it is first the energy which is required to eject electron from the metal surface. And then the next is the kinetic energy. Kinetic energy is the energy which is possessed by due to the motion. So here now electrons, they are just moving from the metal surface, so they are in motion, so they have some kinetic energy with them. So that means you can say that this energy of light, or you can say the energy of photons, it is involved in two things. One is that some energy is required to just remove this electron. That is actually electron is binded with the nucleus, so that's why we just call here it as binding energy. So some energy is here used or utilized to just remove this electron from the metal surface, and then the rest of the energy, that is used as kinetic energy. Now here for this binding energy, it was actually a very important term which you will note down here, that is known as work function. So what is actually work function? So work function, you will remember, it is represented by W naught, and this work function, it is simply the minimum amount of energy required to remove minimum amount of energy that is required, minimum amount of energy required to eject electron from the metal surface, right? To eject electron from the metal surface, So that is your work function, metal surface. So that means this binding energy, you can just call here it as a work function. So that means some amount of energy that is actually utilized here, that is actually involved here in the ejection of electron. In order to remove electrons, some energy is required. But now some energy of this photon, or we can say the energy of light, when some energy is used to remove the electron, then the rest of the energy, it is utilized as kinetic energy. So, and you know that kinetic energy is always equal to 1/2 of mv square. Okay, so that means I can just write it like this. That is the energy of photon. Let's say energy of photon is represented by E. So it is equal to work function, that is W naught plus kinetic energy. So have you written down this? Energy of photon. So this E is the energy of photon. E is the energy of photon. So energy of photon, it is always equal to energy of photon. It is equal to work function plus kinetic energy. So now let's see it in detail. So now the energy of photon. So can I write in place of, okay, it was just E is equal to at W naught, then kinetic energy. Now we know that according to Planck's quantum theory, energy is equal to h nu, isn't it? E is equal to h nu. Then now work function is equal to h nu naught. So what is this nu naught? I hope you remember. What is this nu naught? Can you tell me? Satish, can you tell me what is this nu naught? It is the threshold frequency, isn't it? It is the threshold frequency. And then kinetic energy, that is equal to 1/2 of mv square. Correct? Now, I can also rearrange this like this. That is h nu minus h nu naught. So that will be equal to 1/2 of mv square. Can I write it like this? I have just taken this h nu naught on this left side, so it will become minus. So then h and h Planck's constant, I will just take it common. So what will be inside? It will be nu minus nu naught, correct? Nu minus nu naught. So that's equal to 1/2 of mv square. So this equation is very important. It is known as Einstein's photoelectric equation. So that's why this equation is very important. And with the help of this equation, we can just calculate the frequency. We can just calculate the threshold frequency. We can also calculate the kinetic energy. And here we can also calculate the work function. So Einstein's photoelectric equation. So this is known as Einstein's photoelectric equation. Einstein's photoelectric equation. So in short, you will remember that h nu minus nu naught is equal to 1/2 of mv square. And what is here nu naught? You already know nu naught, it is the threshold frequency. I have told you that threshold frequency, it is the minimum amount of frequency that's actually required to eject electron from the metal surface, right? Yes. So this equation will be very important, Einstein's photoelectric equation. I hope that you will remember this equation. It's very important. Similarly, you can just also remember this one. We can calculate the work function. So can you tell me, for example, if I'm having few metals, let's say I'm having potassium, rubidium, and cesium. Can you tell me among these, which will have very high threshold frequency, which will have very high work function, and which will have very low work function? So can you tell me? Amrisha, can you tell me which among these three can have very high work function? If I have to just write order of work function. Can you tell me? Which will have very high work function? Simply means amount of energy required to remove electron from the metal surface. So very high work function will be possessed by this potassium. Cesium will have very low work function. That means it will require minimum energy to eject the electron from its surface. Got it? You have to remember this, that potassium, its work function will be very high as compared to rubidium, and this rubidium will have very high work function as compared to cesium. So that is why cesium, it easily shows photoelectric effect. I have already told you this. I hope you remember that this cesium or cesium, it shows easily photoelectric effect, right? That means its electron can be easily removed from its surface. So that means it easily shows photoelectric effect. So have you noted down this?
Sir, 1 minute, sir.
Okay, you just note it down. But Jitesh, Ananya, and Amrisha, and similarly, Arvindha, they are not responding me here.
No, sir. I'm writing them.
Are you getting?
Yes,
Yes, sir. Yes.
Okay, then you should also respond me. So we have just noted down this equation. This will be very important, known as Einstein's photoelectric equation. So simply you remember that this cesium, it has very low work function. Work function is here important term represented by W naught. I told that it is the minimum amount of energy required to eject the electron from the metal surface. And similarly, what is nu naught? Nu naught is the threshold frequency. That is the minimum amount of frequency required to eject the electron from the metal surface. So there is little difference. So this is the frequency here. This is the energy here. So that means minimum energy among these three metals, which will require minimum energy in order to show the photoelectric effect. That will be definitely the cesium. Cesium shows easily photoelectric effect, right? But potassium, it requires a lot of energy. So that means its work function is very high. Okay, let's move ahead then. So now you know this Einstein's photoelectric equation and the Planck's quantum equation. So can you solve questions on this? For example, you know that E is equal to NH nu, and similarly, you also know that energy of photon, it is equal to work function, and similarly the kinetic energy. And you also know that H nu minus nu naught is equal to kinetic energy. So these three equations are very important. On these questions are asked. For example, if I will just write a question that calculate energy of 1 mole of photons. So can you calculate? You are just having 1 mole of photons and you have to calculate its energy. So how to calculate? Simply you will write here that E is equal to NH nu, right? You have to calculate the energy of 1 mole of photon. Calculate energy of 1 mole of photons having frequency. Frequency is given to you having frequency 10 raised power 10 hertz. So can you calculate this one? Just try yourself, then I will explain it. So have anybody solved this?
They have to calculate
What is the answer?
multiplying 7.
How much?
Multiplying 7 1 minute again.
Okay, you just multiply it. See, actually,
Sir,
what you have,
frequency is just 10 per 10.
it is 10 raised to power 10 hertz. Okay, see here, you have to
Sir,
calculate energy.
6.626 into 10 power minus 24.
Okay, see here, we are given 1 mole of photon. So 1 mole means Avogadro number. So that is N value is here 6.022 into 10 to the power 23. And then you will multiply it by Planck's constant, that is 6.626. And you will multiply it by 10 to the power minus 34 joule second, right? And then we are having the frequency is 10 raised to power 10 hertz. Hertz you can write per second. So second and per second will cancel. So it will be only in joules because we have to calculate the energy. So, okay, now what will be the answer here? So it is now 6.6.
39.8.
You can just take it as 7. You can just take it as 7. And similarly, you can just take it as 6. So you can just write 6 into 7. And then it will be, now see here, it is 10 raised to power 23. And then here it is 10 raised to power 10. So that is when base Arsam power should be added. So that is 10 raised to power 33. And it is 10 raised to power minus 34. So it will just become 10 raised to power minus 1, right? So it will become 42 into 10 raised to power minus 1. And it is in joules. So you can get the final answer as 4.2 joule. So have you got it now?
Yes, sir.
Any doubt here?
No, sir.
No, sir.
Okay, have you noted down this? Shall I move to the next page?
Yes, sir.
Okay. So for example, now if question is asked like this, that calculate energy of 10 photons. Now it is given that photons are only 10 and whose wavelength is given, whose wavelength is 3.2 centimeter. So can you calculate this? Can you solve this one? Have anybody solved this one? So first, what is given? Given is wavelength. So wavelength is given 3.2 centimeters. So first you will change it into meter. You will convert it into meters, right? So 1 centimeter, 1 meter, that is equal to 10 raised power 2 centimeter. But here it is given centimeter. So 1 centimeter is equal to 10 raised power minus 2 meter, right? So that means you will write 3.2 into 10 raised power minus 2 meter. Now it is easy to calculate. We know that E is equal to NH nu. And we also know that nu is equal to C by lambda. So you will write C by lambda here. NhC by lambda. So what is here n? N is here given, that is the 10 photons. And then what is the next? Next is the Planck's constant, that is 6.626 into 10 raised power minus 34 joule second, right? And then what is the C? Speed of light, that is 3 into 10 raised power 8 meter per second, right? Ten to the power 8 meter per second. And then you will just divide it by wavelength.
I'm seeing it.
Is my voice audible?
Sir.
Again, same thing happened. Amrisha, you just do the same thing, that is make me host so that I can share the screen. Okay. So have anybody solved that question? So can you tell me what was the question? We have to actually calculate the energy, and it was actually n was given number of photon, that is 10, and similarly h Planck's constant, that is 6.626 into 10 raised power minus 34 joule second, right? And then it was the speed of light, that is 3 into 10 raised power 8 meter per second, right? And then we have to actually divide it with the wavelength. So what was the wavelength given? Can you tell me what was the wavelength given?
3.2 10 power minus 2.
3.2 into 10 raised power minus 2 meter, right? Okay. So tell me what will get cancelled here. Meter and meter will cancel. Similarly, second and per second. So answer will be in joules. So our question is correct. So now you can easily see it is 3.2 ones are and 3.2 3.22s are, that 6.6. So it will be just 3 2s are 6. You can just calculate the approximate answer. So that will be 6 into 10. Now see here, it is 10 raised power minus 34. And it is here also 10 raised power 1. So that is your 10 raised power minus 33. And then it's also 10 raised power 8. So what it will come out? 34, you have to just 34, you have to subtract a 9 from this, right? So it will be how much? 10 raised power? Can you tell me it will be how much?
25, sorry. Minus
24.
24 or 25?
No, sir, 25, 25.
So it will be 10 raised power minus 25, right? Is it correct now? Have you got it?
Yes, sir.
Sir.
Yes. So this is
Sir, but,
how to solve
10 power,
questions on
sir, but there's a 10 power minus 2 down.
10 raised power minus.
The denominator.
Exactly. Denominator, we are having 10 raised power minus 2. So when it will just move up, it will become plus 2. So that is 8 to
Minus
10, 11. So exactly, it will be now 10 raised power
minus 23.
minus 23, right? Exactly. Okay, so similarly, if sometimes kinetic energy is given to you and also the frequency, so can you calculate the work function? For example, if I will write it here, that if frequency of electromagnetic radiation is 10 hertz and the kinetic energy of ejected electron is 20 meter per second. Kinetic energy is 20 joule. So can you calculate here the work function? Calculate work function, that's W naught. If frequency of electromagnetic radiation is 10 hertz and the kinetic energy of ejected electron is 20 joule, you have to calculate the work function. So how to solve this? Can anybody tell me how to solve this? Which equation which we will use here? Can you tell me which equation we will use here? We know that we are having the energy is equal to work function, that is W naught plus kinetic energy, right? Isn't it? And now we also know that this energy is also equal to energy is equal to h nu, right? Energy is equal to h nu. So nu is given to you, frequency, and kinetic energy is also given to you. So can you calculate this work function? Just try it. So have you noted down this? Shall I move to the next page?
Yes, sir.
Okay, so see here, we are here given the frequency. So first, let you write this h nu is equal to work function, that is W naught plus kinetic energy. And now here, h is the Planck's constant, that is 6.626 into 10 to the power minus 34 joule second, right? And then it is the nu is given to you. How much is the frequency given? That is 10 hertz. That is hertz. You can write in place of hertz, you can write per second. So that is equal to work function. Work function you have to calculate. So keep it as such. And then kinetic energy is also given to you. That is 20 joule, right? Have you got it? Now see here, per second and second it will cancel. And similarly, and joule will not cancel here. Now see what you have to calculate. You have to calculate the work function. So can I write it like this? It is 10 raised power 1 here, and here it's 10 raised power minus 34. So that means it is 6.626 into 10 raised power minus 33. So now it is here 20 joule. So when I just take it on this left hand side, it will become minus 20, right? Minus 20. So that will be your work function W naught. So that means it is 6.626 minus 20 into 10 raised power minus 33. Got it? So now you can also write it like this. That is, you can write 66.26 into 10 raised power minus 1, right? Into 10 raised power here minus 33. And you can just write here minus, that is 66.26 minus 20, right? Okay. So what will be the answer? Answer will be here. That is 46.26 into 10 raised power minus 34. This will be also in joule, because work function is what? Work function is the minimum amount of energy required to eject an electron. So work function unit will be also joule. So have you got this one? Is there any doubt in this question? You can let me know here.
No doubt, sir.
Okay, so is it clear?
Yes, sir.
Okay, then let's move ahead. So I hope that you can now solve questions on this. So let's then move ahead. Another very important topic we have to discuss here, that is the atomic spectra. I hope that the questions are the numericals which are given on your NCERT text. You will first of all try yourself. Then if there is any confusion, you will let me know in the next class. So let's see what is atomic spectra. We have to discuss next topic, that is the atomic spectra. That is actually, this is the topic which actually comes in this spectroscopy. Spectroscopy is actually that branch of chemistry which deals with the study of interaction of matter with radiation. So let me write it here, that spectroscopy, it deals with the study of interaction of matter, with electromagnetic radiations. Okay, now see here, one of the best example of this spectra, that is actually when you just pass a white light. I hope you have just seen this, that is the diffraction, right? When white light is just passed through a prism, what happens? It just gets split into band of 7 different colors, right? We get here the band of 7 different colors. That's actually your, here we are having VIBGYOR. We just call it as VIBGYOR, VIBGYOR. So that means a red light, it is just above. Above here, it means that it deviates least, and this violet, it deviates maximum. So this is very important point to be noted down, that when a white light, it is just passed through a prism. So it is just your here, this is your prism. And when white light is passed through this prism, we get just band of 7 different colors, which you can just see on a photographic film here. Let's say this is my photographic film on which you observe these 7 different colors. So this band of 7 different colors, it is known as spectrum. It is known as spectrum. So spectrum simply means we are having band of 7 colors here, right? Band of 7 colors. So band of 7 colors. So that is your spectrum here. Band of 7 colors. So this is just one of the examples, just as you have seen in case of rainbow. In case of rainbow, there is also the spectra you can see. That is the band of these 7 colors. So rainbow is one of the example of spectra, or what we call as spectrum. So simply I told that when a white light, it is just passed through a prism, it gets splitted into 7 different colors. That is your VIBGYOR. And this splitting of white light into 7 different colors, that's actually known as dispersion of light. So here we get this band of 7 different colors. This is actually known as spectrum. And this spectrum, it is actually studied in an instrument that is known as spectroscope. So we just study this spectra in case of with the help of this spectroscope. So spectra is always studied with an instrument, that is your spectroscope. So actually this spectroscope, it contains prism inside this, and there is also the photographic film on which we can see these band of 7 different colors. Now here, the very important point to be noted down is that when a white light is passed through a prism, which color deviates least? So can you tell me which color deviates least? So red color deviates least, isn't it? Red color deviates least. You can see here the angle is very small in case of red color. But which color deviates most? Which color deviates most? That is actually your violet, isn't it? Violet I have shown here below. So that means you will remember that this violet color, it deviates maximum. So violet color, it shows maximum deviation. Got it?
Sir,
Maximum. Okay, so shall I move to the next page? This is very important point to be noted down here, that red color deviates least and violet color, it deviates maximum. It shows maximum deviation. That means it bends very much, because actually see, red is having very high wavelength but short frequency. But in case of violet, violet is having very short wavelength but very high frequency, isn't it? So shall I move to the next page?
Yes, sir.
Okay, so now what is here? We're having actually 2 types of spectra. We will study the 2 types of spectra. One is known as emission spectra, another is known as absorption spectra. So let's see first what is emission spectra. Emission spectra. Another is known as absorption spectra, which we will study ahead, but first we will study what is emission spectra. So in case of emission spectra, what we are doing, we are just taking a source. We are just taking a source. For example, let me give example of sodium. For example, this is my, let's say this is a piece of sodium. Sodium, its symbol is Na, right? Atomic number 11. Now, if I just heat the sodium, what will happen? The electrons will absorb energy and they will just move from ground state to the excited state, correct? You have to remember that we are having 2 types of states. For example, let's say this is my nucleus. If electron is very close to the nucleus, let's say it is in the first shell. We're having different types of shells. We will study them ahead. Let's say this is the first shell, then this is the second shell, this is the third shell. I hope you have studied Bohr's model in class 10th, 9th class, right? Okay. Now tell me, when I will just give energy to this electron, that means when it is heated, when this electron it is heated, when this sodium is heated, electron will jump. It will just move in the higher shells. So you already know the first shell is K, isn't it? Then L, then M, N, and O shell. So electron can move, it can jump into higher shells. It can go into L, it can also go into M, it can also go into N. It depends upon the energy. So that means this K, it was the ground state. This K, it was just the ground state, and this O and these other higher states, they are just your excited states. Excited state. So when actually what happens now, when you just heat the sodium, electron gets excited. And when now this electron, it comes back, it will emit radiation in the form of light. So when this electron, it just comes back from the excited state to the ground state. Why it comes back? Because in the excited state, it's unstable there. So that's why electron, it comes back. When this electron comes back from, let's say, O shell to the K shell, it will emit radiation. And that emitted radiation, that is actually just first passed through the slit. So can anybody tell me what is this slit? It is a small cut, or you can say it is a small hole inside in the metal plate, so that we can just get a beam of this radiation. And when it is just passed through a spectroscope, and what is in the spectroscope? In the spectroscope, we are having just a prism, and then we are having a photographic film here. So we can see the various colors on this photographic film. So when actually this sodium, it is heated and then it is actually studied in the spectroscope. So these two things, that is the prism and this photographic film, they are actually present in the spectroscope. So what you observe here, we observe two yellow lines. We observe two yellow lines. So I will just show it here. So let's say this is my one of the line here, and let's say this is my another line. So it is at 589 nanometer, and second line it's observed at, let's say, 589.6 nanometer. So they are just having different wavelength. They are obtained at different wavelengths. Otherwise, both these are two yellow lines. So in case of sodium, what we get two yellow lines in its spectra, two yellow lines. So you have to remember this. It is given on your text that when we just take the spectra of this sodium, we just get the two yellow lines, and they are at wavelength of 589 nanometer and 589.6 nanometer. So this is the spectra of sodium. Similarly, you can also take the spectra of potassium, spectra of lithium. Different elements give different spectra. For example, in case of sodium, you are getting two yellow lines, but in case of potassium, you are getting violet lines. And in case of lithium, you are getting, let's say, purple lines. In case of another element, you are getting different lines. Sometimes you may get one line, one color. Similarly, sometimes you can get two colors, sometimes you can get three colors. So different elements give different emission spectra. That is why it is just like the fingerprints. So that's why it's very important. This atomic spectra, it is just like the fingerprint. Okay, I will write it here, that this atomic spectra, it is also known as line spectra, because we actually here get the lines, right? Line spectra. So this atomic spectra, or what we called as line spectra, it is just like the fingerprints. It is just like the fingerprints. As you know that each person has different fingerprints, right? Fingerprints do not match. Every person has a unique pattern of fingerprint. So that's why different persons have different fingerprints, so they can be easily identified by DNA technology, DNA fingerprinting, right? Similarly, elements can also be identified with this atomic spectra, because every element has a different spectra. The spectra of two elements will not match. It's totally different. So that is why this is very important. I hope you will remember it, that the emission spectra, or what we called as line spectra or the atomic spectra, it is different for each element. We are having 118 elements. So that means every element has different emission spectra. So that means we can just identify these elements with these spectrums. So that is why whenever a new element gets discovered, we just first find its spectra. If spectra matches with any of the elements which are already discovered, so that means we have not discovered a new element, it is just same. But if the spectra comes out to be different, so that means it is the new element, it is a different element. Because spectra of two element, it cannot match. All the elements have different spectra. So have you got it? Have you noted down this? Shall I move to the next page so that I can give?
Yes, sir.
Yes, sir.
Okay, so for example, okay, let's now see the spectrum of, hydrogen. So for example, I'm having the first element of the periodic table, that is my hydrogen. So if I have to just to take the spectra of this hydrogen, what we do here, we just take this hydrogen gas in a closed, let's say here we are having this closed container, and inside this we have just placed this hydrogen gas. Now we are just giving silent electric discharge. So here we are just giving slight electric discharge. So that means we are just passing current, but very low current, which will not actually produce spark. silent electric discharge. So that means, let's say this is your positive pole, it is connected to the positive terminal of the battery. And let's say this is your negative pole here. And this is just connected to the negative terminal of the battery. So when you just give this energy, when you just pass this electric current inside this hydrogen gas, so what will happen? There will be also excitation, isn't it? Just as I told that electron, when it absorbs energy, it will jump into higher energy levels, or what we call as shells. Just for example, let's say hydrogen, its nucleus is this. Then it is the, let's say, the first shell in which we are having this electron here. Now, what when we just give energy to this electron, what will happen? It will jump. It is ground state. So this is the K. Then the next it will be your L, isn't it? Then it will be your M shell. Then it is also your N shell. So we are having various other shells. So K is just your ground state. And now when you just pass this silent electric discharge with the help of these two metal plates, they are connected to the positive and negative terminal of the battery. What will happen? This electron will jump. Either it can go into M, it can also go into this L, M, similarly into N. It can move into any shell. It depends upon the energy, how much energy you are giving. Now, when it just goes into these shells, so they are what? They are your excited states. They are your excited states. Excited state means which has very high energy. We know that K has very low energy, then L has higher energy, M has very high energy, and similarly N, it has very high energy, N shell. So that's why electron, it moves upwards, it jumps into higher shells because we are just providing energy. But in these excited states, electron is unstable. So what it will do? It will just come back to its ground state. Let's say this electron, it's coming back. But when it comes back, it will just emit radiation. It will just emit radiation. So that radiation emitted, that is actually, first of all, here pass it through a slit, as I told. Let's say here it is the slit, a small cut in a metal plate, and then this radiation, it is just passed through a spectroscope, in which actually we are just having all these in a spectroscope. And in this spectroscope, what we are actually having? We are having a prism. Prism is there in the spectroscope. So there will be now diffraction. That means when this radiation, it just passes through this prism. And there is also the photographic film, we get the various colors. So can you tell me, when we just take the spectra of this hydrogen, how many colors are visible in the visible region? We are first of all having here the violet color. Then the next is blue. The next is yellow. Then the next is red. So that means we get the 4 different colors in the spectra of hydrogen. So when we just studied the spectra of sodium, we got only 2 yellow lines, right? But in case of hydrogen, we get here the red color. We also get here the blue color, right? Similarly, we also get the yellow and violet. Let's say this is your yellow, and let's say this is your violet here. So we are just getting the 4 different lines, 4 different colors here in the spectrum of hydrogen. So this is the hydrogen spectrum. So that is why I told that each and every element have different spectra. So the spectra of 2 elements cannot match. It is always different. And that is why I told that this spectra, it is just like the fingerprints. So you have to remember this, that spectra is like the fingerprints. So that means as the fingerprints are different, so the spectra of each and every element is also different. So have you got this? This is a very important concept here, that for example, let's say we are having 118 elements, isn't it? Now let's say a new element was discovered whose atomic number is 120. Let's say new element we have discovered whose atomic number is, let's say, 120. Now I am telling that it is the new element which I have discovered, but First of all, its spectra will be taken. If the spectra matches with any of these 118 elements, so that means it is not the new element. But if the spectra doesn't match with these 118 elements, so that means it is my new element. So this is how actually new elements are discovered and how they are matched with the previous elements which are already known to us. So this is the very important point to be noted down, that the atomic spectra, or what we called it as line spectra, it is just like the fingerprints. Just as the human beings have different fingerprints, we can identify them, we can differentiate them on the basis of the DNA fingerprinting. So same is the case in case of elements, they are also having different spectra. So have you noted down this? Is it clear? Any doubt here?
No, sir.
Okay, so that means, for example, in case of sodium, we are getting 2 yellow lines, but in case of potassium, we are getting, let's say, violet lines, and in case of lithium, we are getting purple line. So different elements will give different spectra, and it is actually observed with the help of instrument that is known as spectroscope. Okay, then let us see, next is your absorption spectra. One was the emission, another is absorption spectra, correct? Absorption spectra. Now what we do in this absorption spectra, we are just having a white light and we are passing it through a substance. Okay, let me show it here. For example, let's say I'm having sun here. Sun is just my source of white light. So let's say I'm having this white light here coming from the sun. And then this white light, it is actually passed through solution of the substance whose spectra is to be taken up. So I will just, let's take the same sodium. Let's take the absorption spectra of sodium. So for example, let's say I'm here having sodium, that's your Na. I have just taken the solution of this sodium, right? This is the simply solution of sodium. Now, when we just pass this white light through this sodium, what will happen? It will just absorb some colors. Actually, do you know that this white light, it is actually made up of 7 different colors? That is your violet, indigo, blue, isn't it? Green, yellow, orange, and red. So when you just mix these 7 different colors, you get a white color. Is it correct? Have you got it? White color, you will remember, it is not a single color, it is a mixed color. It is actually mixture of 7 different colors. So that is your violet, indigo, blue, green, yellow, orange, and red. So when this white light is passed through the sodium, so sodium will just absorb a few radiations, few lights, and it will then emit some radiation, right? It will then just transmit some radiations, and that transmitted light, it is actually now passed through a prism that is actually in the spectroscope. And here the spectra taken, that is actually observed here on the photographic film. So that will be your absorption spectra, because some radiations are actually here absorbed, and this is the transmitted light. So here transmitted light is actually studied in the spectroscope. So have you got the difference? Transmitted light is actually studied in the spectroscope. Transmitted light. So when you just see the transmitted light here, what you will observe? You will just observe, do you remember that in case of sodium, when we just have taken the emission spectra, we have got the 2 yellow lines, correct? Do you remember that we have got the 2 yellow lines? In the emission spectra of sodium, we have just got the 2 yellow lines. But here, in case of absorption spectra, we will just get here the dark bands. So these are 2 dark bands. So what does this dark band mean? What does it indicate? It indicates that it has just absorbed these 2 colors, that is those yellow colors. So what it will emit? It will just the spectra here, which is observed here, that will actually consist of which colors? So can you tell me which colors will be observed here? You will just observe, let's say we are here having violet, then indigo, then blue, then green. Yellow will not be observed here, orange and red, because yellow has been absorbed by this sodium. So solution of sodium, you will remember that it absorbs yellow light. Got it? So is it clear what is the difference between emission and the absorption spectra? Any doubt here? Meghna, can you tell me, is it clear?
Sir,
Yes, so you have to just remember that in case of emission spectra, we are just directly passing the radiations in the spectroscope and we are just getting the spectra as it is. But in case of absorption spectra, what we firstly do, we just pass the white light through the solution of that substance whose spectra is to be taken. And then the transmitted light is actually passed through the prism and the spectra taken on the photographic film. So that will be your absorption spectra. So this is just your photographic film here. Photographic film. So that means you will simply remember that in case of this absorption spectra, those colors are those lines which are actually absorbed by the substance. They will be here dark spots, dark bands will be observed at that spot. Have you got it? For example, yellow color was absorbed by the sodium, so that's why at yellow we are just getting the dark band. So in case of absorption spectra, we just get some dark lines or the dark band in the continuous spectra, in the otherwise continuous spectra. So is it clear? So this was the absorption and the emission spectra. Now let's move ahead. Next, we have to actually study in detail the spectra of hydrogen. Hydrogen spectrum. Okay, I will write the heading, hydrogen spectrum. Now, in case of hydrogen spectrum, we get various types of lines, not only those which we have observed, they were actually in the visible region, which we have observed, that is violet, blue, isn't it? Yellow and red, they were only in the visible region, but we observe various lines in the spectra of hydrogen, and those lines, they have been actually classified into various series. So number first is known as Lyman series. So it is actually observed in the hydrogen spectrum, Lyman series. Now next is your Balmer series. These are actually names given to different series which are actually observed in the spectrum of hydrogen. So the third one is Paschen series. You have to remember as such as it is. So the next is Brackett series. Brackett series. And similarly, next is Fund series. P will remain as silent. Fund series. And the next is Humphrey series. Next one is Humphrey series. So these different types of series are observed in the spectra of hydrogen. Now, actually here, first of all, Balmer here came. Balmer, actually, it is the name of the scientist who have actually observed these. So he gave the formula that is known as Balmer's formula. Balmer's formula. With this Balmer's formula, you can just calculate the wave number. So wave number, that is nu bar, it is always equal to 1 by lambda. So he gave the formula that it's equal to 109 677. This is the constant value. And then it is 1 upon 2 square minus 1 upon n square. So this is the formula given by Balmer, known as Balmer's formula. So you will remember this Balmer's formula. So now what is here, this new bar, it is the wave number. And this is the lambda is the wavelength 109677. It is actually a constant value. I will just tell this, it is actually known as Rydberg constant. So, okay, this was the Balmer's formula, but this Balmer's formula you can only apply for this Balmer series, which is actually observed in the visible region. But all other series, they are not observed in the visible region. For example, Lyman series, it is observed in the UV region. Then this Paschen series, it is observed in the IR region, that is infrared region. So actually, another scientist came whose name was Rydberg. So he gave the formula known as Rydberg's formula. This is very important. Rydberg's formula, we can apply it anywhere on all these series. So Rydberg formula is what? That is same new bar, that is the wave number. It is equal to 1 by lambda. And that is equal to Rydberg constant, that is RH, and then 1 upon n and 1 square minus 1 upon n 2 square. And 2 square. So now what is the here value of RH? That is the Rydberg constant. It is same, that is 109677. You have to remember this value. Just as you have remembered the Planck's constant, as you have remembered the Avogadro number, similarly, you will remember this Rydberg constant, that is RH. So this Rydberg constant, it is always equal to 109677. And this wave number, it will be in centimeter inverse. Unit will be centimeter inverse. Got it? You have to remember this formula. Rydberg formula, it's very important. Rydberg formula is very important. With this Rydberg formula, you can just calculate the wavelength. You can just calculate the wave number. Similarly, you can just calculate the frequency of any of these series. Now let's see this on the next page. Have you noted down this?
Sir, 1 minute, sir.
Yes, sir. Noted, sir.
Okay, you just complete it. So when we just take this hydrogen in the spectroscope, we just observe these different types of lines, or what we call the different types of series. So the first is Lyman series, next is Balmer series, next is Paschen series, next is Brackett series, next is Fund series, and next is the Humphrey series. So let me tell that in which region they actually are, and what is here N1 and what is here N2. You have to note down this N1 and N2 is, it is 1 upon N1 square minus 1 upon N2 square. Now what is this N1 and N2 for all these series? We will just check it out on the next page. So let me write it here. So you will remember that first was what? First was the Lyman series, right? So Lyman series, it is first of all observed in UV region, that is the ultraviolet region. And next you will remember that for this Lyman series, N1 value is 1 and N2 value can be anything that is greater than 1, that is 2, 3, 4, 5, 6, 7, etc. So got it? Similarly, for the next, that is your Balmer series. Balmer series. For Balmer series, you will remember that it lies in the visible region. It lies in the visible region, which we have actually observed. When I just told that this is the spectra of hydrogen, I told that we just observed the 4 colors. That was the violet, blue, isn't it? Yellow and red. So these 4, they are actually observed in this visible region, that is your Balmer series. In this Balmer series, N1 value, that will be 2, and N2 value, it will be your 3, it can be 3, it can be 4, it can be 5, etc. And similarly, the next, what was the next series? Paschen series. So Paschen series, it lies in the IR region, that's infrared region, IR region. It lies in the infrared region, and here N1 it will be 3, and N2 it will be here 4, 5, 6, 7, etc. Got it?
Sir, is IR infrared?
Yes, IR is the infrared region.
Okay.
Infrared region. UV is the ultraviolet region. This is the visible region. This is the infrared region.
Okay.
We have seen these in the electromagnetic spectrum. Okay, Lyman series, then Balmer, Paschen, and then it is the bracket series, right? Bracket series. So in case of bracket series, it lies also in the infrared region. That's IR. It lies in the infrared region. And here N1 value, that will be 4, N1 value will be 4, and N2 value will be greater than 4, that is 5, it can be 6, it can be 7, etc. Similarly, then the next is your fund series. Fund series, it lies in the this lies in the 4 infrared region. Here N1 value is 5, and N2 value is here 6, 7, 8, etc. Next is the Humphrey series, and it lies in the also very far infrared region, very far infrared region, that's IR. So that means except the first two, all other they lie in the infrared region, and here N1 value will be 6, and N2 value here it will be 7, 8, 9, etc. So this spectrum of hydrogen, it is very important. Sometimes here questions are asked in the NEET that what is the N1 value, what is the N2 value for, let's say, for bracket series, for Balmer series. Balmer series lies in which region? So it is asked. So this is very important. I hope you will remember this table. This is very important. It is also given on your textbook. Like, so the first series which we observe in the spectra of hydrogen, that is the Lyman series. The next is the Balmer series. Next is the Paschen series. Next is the bracket. Then the fund series. We will here remain silent. We will here remain silent series. And then the next is Humphrey series. So the first Lyman series, it lies in the UV region, and the Balmer series, it lies in the visible region. Then all other, they lie in the IR region, infrared region. Next is their N1 and N2 value. So I hope you will remember that N1 here it's 1, N2 here it's 2, 3, 4. Similarly, for Balmer series, N1 is here 2, and N2 is here 3, 4. So that means you will simply remember that N2 is greater than N1 always. N2 value, it is greater than N1. So is it now, have you got it now? Have you noted down this?
1 minute, sir.
Okay, you just note it down because this table, it will be very important. And this is the actually where from questions are asked in the competitive exams. Numericals will be asked on this Balmer's formula and the Rydberg. So man is the actually Rydberg formula, but you should remember that first it was given by the Balmer, that is the Balmer's formula. And in case of Balmer, N1 will be 2, right? This is very important, and it lies in the visible region. That means you can see it. The colors here you can see in the visible region. In other regions we cannot see. And N2 value is always greater than N1. So have you noted down now? Have you completed?
Sir.
Okay, so now what is the Rydberg formula? That is actually very important here, which we have to note down and which we have to actually apply in the questions. So Rydberg's formula, it is just what you can calculate with this Rydberg formula. You can just calculate the wave number. So wave number is always equal to Rydberg constant, that is RH. and it's always equal to 1 upon n1 square. So I told that what is the n1 value for different series, and up minus 1 upon n2 square, correct? Okay, so tell me that for example, let's talk of, let's say here n1 value is let's say 2, that is your Balmer series, and n2 value, let's say it is 3. Yeah, okay, let's say it is 4, and 2 is 4. So then can you calculate wave number for this series? Can you calculate the wave number? So it will be a Rydberg constant. What is the Rydberg constant value? You already know it is 109677, or some books write it as 109678, but on the text it is 677. So you will remember as such, and here it is in centimeter inverse. So just write it down that it is 109677, then it is 1 upon n1 square. So what is n1? That is 2 square, right? Minus 1 upon n2 square, so that is my 4 square here. Okay, then this answer will be in centimeter inverse. Okay, now you can solve this, right? 1 upon 2 square, that is your 4, minus 1 upon 4 square, that is 16. So when you just cross multiply, it is 16 minus 4, that's your 12 upon 64, right? 109677. Here it's also 109677. And when you will just multiply this 109677 with this 12 upon 64, you will get the wave number in centimeter inverse. Got it?
Sir.
Any doubt here?
Sir.
Okay, so I hope that you can now solve it yourself, that you have to just multiply this 109677 with 12 and then divide it by 64, you will get the wave number. Now, when you have just got the wave number, what you can calculate then with this wave number? You know that wave number is equal to 1 by lambda, so you can calculate the wavelength, right? And when you just calculate the wavelength, you can also calculate the frequency. We know that frequency is c by lambda. And when you just calculate the frequency, you can also calculate the energy, because we know that energy is equal to h into nu. So that means with this Rydberg formula, we can calculate various values. We can calculate the frequency, we can calculate the wavelength, we can calculate the wave number, we can calculate the energy also. So that is why it is very important to remember this Rydberg formula. So I will repeat it. It is nu bar is equal to RH 1 upon n1 square minus 1 upon n2 square. So n1 and n2, it is different for different spectral lines, which we have already discussed, right? So have you noted down this?
Sir.
Okay, so let's recap what we have studied. So today we have just started with the Planck's quantum theory. It is application that how it actually explains the black body radiation and the photoelectric effect. So in the black body radiation, I just told that whenever iron rod it is heated, it first becomes red, because red is having very low energy. And red can easily be produced, because it requires very minimum frequency, or what we can say, it requires minimum energy. Red is having very low energy. Then when we just give more and more energy to this iron rod, then it can become orange, it can become yellow, it can become similarly green and blue. So it depends upon the energy, because according to Planck's quantum theory, energy is directly proportional to the frequency, and that is frequency decreases when we just move from violet towards the red. And the next was the photoelectric effect, and in that you have to remember the Einstein's photoelectric equation. And according to Einstein, he told that when light is actually fall down on a metal surface, what happens? Some of its energy is utilized in the ejection of electrons, and the rest of the energy that will act as kinetic energy. So that means we can just calculate from the Einstein's photoelectric equation, we can calculate the work function, we can calculate the kinetic energy, we can calculate the threshold frequency. So all these terms can be calculated. So they are very important. That equation is very important. That is actually H nu minus nu naught, that is equal to kinetic energy. Next, we studied related to the spectroscopy. So spectroscopy, I told that it is that branch of chemistry which deals with the study of interaction of matter with radiation. So that means when any radiation, it is just fall down on the metal surface, how it will interact with this. So that is actually studied with the help of instrument that is known as spectroscope, which actually contains prism in it and also a photographic film. So just as we just take the spectra of sodium, we get the 2 yellow lines, and in case of hydrogen, we get the 4 different colors. We get the violet, we get the blue, we get the yellow, we get the red, but that is in the visible region. So similarly, it is the emission spectra. Emission spectra, it is always what you can say, it is also known as the line spectra, because every element has different line spectra. So it is just like the fingerprints, right? And then I told that what is the absorption spectra. In absorption spectra, what we do, we just first pass the white light through the substance or the solution of substance. It will absorb few radiations, and the transmitted light is then studied in the spectroscope, and the various lines which we actually observe there in the spectra. So that will be your absorption spectra. So just in case of sodium, if we just take the absorption spectra of sodium, we get the various colors, but except yellow, because yellow has been absorbed by the sodium. Similarly, some element can absorb green, some can absorb red, isn't it? Different elements have different spectra. Then we just studied the spectra of hydrogen. So when we just study the spectra of hydrogen, it's very complex. It contains various series. They have been discovered by different scientists. Just the first is the Lyman series. It was discovered by Lyman. Next is the Balmer series, Paschen series, Fund series, Brackett series, isn't it? Then it is the Humphrey series. You have to remember their N1 and N2 value, and you have to remember their visibility region. So that means the Lyman series, that is actually observed in the UV region. And similarly, Balmer series, that is actually lies in the visible region. And other spectral lines, they are actually observed in the infrared region. So next, you have to remember the Balmer's formula and the Rydberg formula. Rydberg is actually the main formula. So that is, we can calculate the nu bar, that is equal to RH, Rydberg constant, then 1 upon N1 square minus 1 upon N2 square. It is in centimeter inverse, because actually here Rydberg constant is having value 109677. It is in centimeter inverse, right? So I hope that you will revise each and every formula here. That's very important. And we will just solve the questions, numerical type question in the next class, and then we will move ahead. Any question, any query, you can just let me know.
No,
No,
sir.
sir.
Okay, have a nice day ahead.
Thank you,
Thank
sir.
you.
Thank you, sir.
Okay, most welcome.